an astronomer, an astrophysicist. This means I look at the stars. It's a pretty good job. What I do is I measure light, so I can count how much light I get, I can count what color it is, and I can work out when I saw the light. And with these three things, when, how much, and what color, I'm going to tell you a story about the most ephemeral thing there is, our universe. It is, at the same time, the biggest thing there is, tautologically, the oldest thing there is, tautologically, but it is ephemeral. And to do anything ephemeral, you need a clock. So I'm going to spend a couple of minutes talking to you about a clock. It's a little bit of an odd clock, but I think we'll get there together. So when you were at school, you got given this exercise. There's a train, it's going at 100 kilometers an hour. How far away did it get in 1 hour? 100 kilometers an hour, 1 hour, it's 100 kilometers away. Sometimes they trick you. You go, there's a train, it is 200 kilometers an hour, it's 200 kilometers away, and it's going at 200 kilometers an hour. How long ago did it leave the station? 200 kilometers an hour, 200 kilometers, it left the station an hour ago. That's the only clock we have. Speed and distance. And for anybody traumatized that they were back at school, I'm terribly sorry. Don't worry, we're not doing that again. That's it. So let's start. It's a nice picture of the universe. Let's start with this fellow here. Now, this guy is called Romer. Well, he was. He worked in Paris. He's a Danish astronomer, and he worked in Paris in the late 1600s. And in the early 1600s, Galileo had pointed a telescope at Jupiter and had seen that Jupiter had moons that went around Jupiter. And this got Galileo into trouble with the church. It wasn't actually an easy thing to get through. But only 60 years later, Romer was doing what astronomers do. When? So you'd look at the moons of Jupiter, and the moons were going around Jupiter, and they seemed to be very regular, as the moons would be. The moons don't care who's looking at them. And he found out that sometimes the moons went behind Jupiter a little bit too soon. And sometimes they went behind Jupiter a little bit too late. And sometimes they came out a little bit too soon, and sometimes a little bit too late. Just from when? Now, what was happening, and Romer worked this out, it's quite spectacular, was that sometimes the Earth is nearer Jupiter. See, both the Earth and Jupiter going around the Sun, and sometimes we're closer together, and sometimes we're further apart. And when we were further apart, the moons were late. And when we were closer, the moons were early. What this means is that light has a speed. And that's quite an important thing. Romer actually calculated the speed of light in the late 1600s, and he got within 25% of the right value. So that's quite remarkable itself. Now, if light has a speed, this means that if you're emitting light and sending light out, the color at which I will see it will depend on whether you're coming towards me or going away from me. Exactly like an ambulance. When an ambulance's siren is coming towards you, the pitch is higher, and as it goes away, it is longer, it's slower. Light does the same thing. If something's coming towards you, the light is bluer. If something's going away from you, the light is redder. Now, I'm an astronomer, so I measure color, and now I have a speedometer. I can actually convert color to speed. Halfway there for my clock. It's pretty good. Now we need distance. So the next person in this story, it's going to be a story told through people, because people do this, is a lady called Henrietta Swan-Leavitt. She should be the third one, if I've got the right slide, yes, indeed. She's the third one from the left, as you look at that picture, studying the plates. Now, Henrietta Swan-Leavitt was working at Harvard. She was educated at Radcliffe at a time in the beginning of this century where women were not allowed to be astronomers. It wasn't allowed. She was absolutely an astronomer, and a damn good one as well. But what she managed to help us do was to calculate distances. So Henrietta Swan-Leavitt was measuring stars that are called Cepheid variables. They get brighter and dimmer. But Cepheid variables have a magic property that they're super, super, super bright. So they're about 10 times more massive than the sun, our sun. They're about 200 times bigger and 15,000 times brighter. So you can see them a long way away. And Henrietta Swan-Leavitt's work allowed us to know exactly how bright these things should be. Now, if something's near you, it's bright. And if something's far away, it is dim. You can do this with a light bulb if you don't believe me, but trust me, it works. So now that we had an absolute measure of how bright something should be, thanks to her work, we could actually work out distances. We're almost there, right? We have speed and distance. So now we need some people to measure it. And now we have our next two heroes, this fellow who was called Vesper Schleifer, who actually measured colors. He's an astronomer. He measures colors. So he measured colors of a lot of galaxies. And he converted them to speeds. And the next fellow, who is Edwin Hubble, who measured distances. He used Henrietta Swan-Leavitt's method, looked for stars that get brighter in galaxies, and measured distances. And these two people gave us a bunch of data. The third, fourth, fifth hero in this story is the guy in the middle of this picture. One side is Einstein, the other side is Millikan. Unless you're a physicist, you wouldn't know who Millikan is, but it doesn't really matter. The one in the middle is Georges Lemaitre. And by the way he's dressed, you can work out that he's a Catholic priest. And in fact, by the early 1900s, the Catholic Church had no problem with the universe. And in fact, they have a really good observatory, the Vatican Observatory, where great astrophysical research continues to be made. But the reason Georges Lemaitre is on this picture and part of this story is not because he was a priest. The reason he's up there is because he was a brilliant mathematician and one of the few people who could actually calculate through Einstein's general theory of relativity. And what he worked out was that the universe did not need to be static. It could be dynamic. The theory allowed this to happen. Einstein, by the way, was horrified. He actually added things into his theory to make the universe static. It turned out he was wrong, but it's okay. So now we have a theory, we have speeds from Schleifer, distances from Hubble, and Lemaitre, and pretty much at the same time Hubble, put all of this together to work out something quite remarkable about our universe. The further away you look, the faster things are moving away from you. Now let's go back to our train, okay? So right now, I look at a train, it's out there going 200 kilometers an hour, and it's 200 kilometers away. And over here is a train that's going 300 kilometers an hour, and it's 300 kilometers away. At this point, you should go, ding, ding, something's happening here. All the trains left the station at the same time. That means if the galaxies are doing this, the universe had a start. And that's quite a remarkable discovery. A universe started. It means it has an age. It is not static. So what is the age of the universe? Well, astronomers encode this how fast things are changing in a number we call the Hubble-Lemaitre constant. We now call it the Hubble-Lemaitre constant. At the time, we just called it something else, but thanks to Hubble and Lemaitre, it's that now. And Hubble and Lemaitre calculated this number, and they worked out it is 600. It doesn't matter what the units are. Don't worry about the units. The number was 600. The units are kilometers per second per megaparsec, but that doesn't really matter for anybody who's really interested. If the number is 600, the universe is 2 billion years old. So the astronomers came out and said the universe is 2 billion years old. And the geologists went, no. We know about radioactivity. The Earth is 4 billion years old. There's no way your universe is younger than our Earth. Since then, astronomers have been trying to get this number more accurate. And the rest of this conversation is about getting that number more accurate. So the next hero of this story is Wendy Friedman. Wendy Friedman is a professor right now at the University of Chicago, and in the early 1990s, used the Hubble Space Telescope, yeah, we named a whole telescope after him, to measure accurately this number. She used Cepheid variables, the Leavitt magic stars, and distances through the colors, speeds through the colors, and she determined, and her colleagues together, the number to be 75. Now, if the number is 75, the universe is 14 billion years old. And that's good. The Earth can be 4 billion years old. There's enough time for the older stars. Everybody's having a good time. It's all fine. And we would stop there. But not quite. Towards the end of the 90s, in 98, two teams of astronomers, I was fortunate to be part of one of them, determined, we were trying to measure how the universe was expanding, and it turns out that the universe is accelerating in its expansion. To make that happen, we had to change what we thought the universe was made of. So what we understand our universe is made of right now is not very much of us. So we, the planets, the stars, the galaxies, the stuff between galaxies, makes up 3% of the universe. That's it. 27% of the universe is made out of some stuff we call dark matter. We don't really know what it is, but it's a good name. And 70% of the universe, we have absolutely no idea what it is, but it has an even better name, which is dark energy. So now we have this stuff the universe is made of, we have a theory, we can actually work some other stuff out. And if you take this picture, which is a picture of our universe when it was a baby. This is literally a picture of the universe when it was 300,000 years old. And because Roma told us the light speed is fixed, it actually means we can look into the past. And this is, indeed, the baby universe. So you take the stuff that we have, you take the theory, you take the baby universe picture, and you say, what is the magic number today? What is the Hubble-Lamette constant today? And the answer is 67.66. Not 75, not 600, thank God, but 67.66. So it's a pretty good number. Excellent. Are we done yet? So the last hero in this story is this fellow. This is Adam Riess. Adam Riess got the Nobel Prize for Physics in 2011 for co-discovering the accelerating expansion of the universe that I told you about before. He was 42 years old when he got the Nobel Prize, 29 when we did the research. And, you know, if you get the Nobel Prize, you could spend the rest of your time just looking at the medal. I mean, it's pretty good. Yeah? But he didn't. Adam decided he'd measure the Hubble-Lamette constant even more accurately. And using Henrietta Leavitt's Seifert variables and speeds, when, how much, and color, that's it, as all of these measurements, he worked out that the Hubble constant here now is 74. And now we get to almost the end of this talk. The baby universe tells us 67.66. The current universe tells us 74. Either we don't know what our universe is made of, or we don't know what the law of gravity is. But what is sure is that our ephemeral universe and the ephemeral stars in it are telling us that our ideas are also ephemeral. Thank you very much.